Hi guys, welcome to our next video lesson. Today we're going to be looking at electric potential difference and basically having a look at electric fields and a look at electric potential energy that's associated with those fields. Now it can be a bit of an abstract concept or a little bit hard to imagine, so hopefully I'll do my best to describe it as we go through so you get a good idea of what's going on. Alright, so electrical potential energy. The best way to think about it is to relate it to something we know, which is gravitational potential energy. So if we look at something like something that over the Earth, so consider a mass m in the gravitational field near the surface of the Earth. Now this is a situation that we're quite familiar with. We know that that mass must have energy due to its position because it's free to fall. If we left it there, it would just sort of fall down, and in which case it would accelerate and it would then have a change in energy. So it must have had some energy due to its position in that gravitational field, and we know that is called gravitational potential energy. So if we think of a positive charge, so plus Q, in its field as we've shown in the little picture here, and we have our small test charge, which is going to be our little Q placed in here. It would be free to move, almost like our mass in the gravitational field would be free to move. But if it's positive, we know that its direction is going to start accelerating in the direction of the field lines, which is away from Q. Now, if it's accelerating, we know that it has to have an increase, or it needs to acquire kinetic energy because it's moving. And we know the conservation of energy, that it can't be created or destroyed, it has to come from somewhere. But where does this energy actually come from? And that's basically the crux of what we're going to be looking at today. So electrical potential energy, where does it come from? Well, any charge that's placed in an electric field has energy due to its position in the field. So we call this energy electric potential energy. So just like an object had gravitational potential energy due to its position in the field, the same is true for charges. So when we have an electric field, we're going to have potential energy of charges due to their position in that field. Whether or not they're close to the big charge, how far away they are, is going to depend how much work and how much energy they're going to have. Now, when we talk about the gravitational potential energy, it's easy to tell if an object is going to gain or lose potential energy. If it starts up high, it's going to have a lot of potential energy. As it starts to fall to the surface of the Earth, it's going to lose that potential energy as it is converted into kinetic and it's moving. So it's quite easy to tell if it's coming towards the Earth, it's going to be losing its potential energy. If it's moving away from the Earth or it's getting lifted or something like that, it's going to have more potential energy. Now, when we have a look at charges, it's a bit harder. There's a few things that impact it. So there's two different types of charges. We've got positive ones and negative ones, and we've also got the direction that it's moving is relative to the field. It's not set like it is around the Earth. So there's a few rules that we can use to help us figure out which direction is going to happen. So if we have a positive charge and it's moving in the direction of the field, so remember if it's following those field lines, it's going to be accelerating freely. And if it's increasing its acceleration, it's going to be gaining kinetic energy. And if it's gaining kinetic, obviously it's going to be losing potential. Alright, just like our mass in the gravitational field. Oppositely, if a positive charge is moving opposite to the direction of the field, it's moving against the force that's on it. It would want to move away, but if it's moving in the towards the charge, if it's positive, or if it's opposite the direction of the field, it must be doing work. And if it's doing work, it has to be gaining electric potential energy. If we look at a negative charge, that's going in the direction of the field. So imagine our little charge in the middle, positive, with the lines radiating away. If we move a negative charge and we push it closer, if it's going in the direction of the field, away from our positive Q, it's going to be moving in the direction of the field. So work is going to be done on it, and it's going to gain electrical potential energy. And if our negative charge moves opposite to the field, which it normally would, it's going to be accelerating freely and gaining kinetic energy, losing electrical potential. So we just have to figure out what's going to happen with our little charge. Imagine if it's moving towards or away from or in the direction of the field or opposite the direction of the field, and if it's positive or negative. And we'll be able to tell if it's going to lose or gain kinetic energy, and therefore potential. Now, electrical potential difference. So it's defined as the difference between 2 points in an electric field is the work done per unit of charge. And we're talking about if we have to move a positive test charge between 2 points. So if everything else stays the same, and we have our field, we're popping in a little test charge, it's going to be how much work has to be done to move it from one place to another. It only works when everything else is the same. It doesn't work if we change the big charge in the middle, or if we change the size of the test charge, or anything like that. But if we're just looking at everything else staying the same, we can work out how much work is done and what the potential difference is. So the potential difference is equal to the work done divided by the size of the charge. And we know the potential difference is another name we can call voltage. So we're looking at the change in voltage, and charge is Q, and work done we abbreviate to W. Now the unit of electrical potential difference is called the volt. Alright, it's fairly common, everyone's heard it before, and work is measured in joules, charge is measured in coulombs. So a volt is always equal to, that's the three-pronged equal sign, 1 joule per coulomb. So it is equal to the volt. An example, how much work is done when moving an electron across a potential difference of 100 volts? So how much work we need to do the Q times by our potential difference. If we're talking about an electron, it's going to have a charge of 1.6 times 10 to the neg 19 coulombs, and it's going across 100 volts. So coulombs, we haven't cancelled it out, so our units of work it's a type of energy, so it's going to be in joules. So we end up with 1.6 times 10 to the neg 17 joules as how much work has to be done. Energy changes. So whenever a charge, we can call it Q, moves between 2 points in a field, its potential energy changes according to the relationship, the same as it was the last time. Instead of having work, it's going to have a change in potential energy. So however much work it does is going to relate to how much potential energy it has either lost or gained. So it's going to be the same formula. So the change in potential energy is the charge times by the potential difference that it has in the position. Now, the law of conservation of energy we've had a look at before. We know that we can't create or destroy energy, and whatever energy is lost has to be gained somewhere else. So we can figure out the work done when a charge moves through a potential difference. We've got the change or increase and decrease in electrical potential is delta PE, and the change or increase or decrease of kinetic energy is delta K. We've got the work is equal to the change in potential energy, which is equal to the change in kinetic energy. If we gain potential energy, we must be losing kinetic energy, and vice versa, and that is all equal to Q delta V. So we can, whichever part of this equation we need, we can just take and use it. Now, the change in potential energy and the change in kinetic energy are included in these modular signs because as one increases, the other decreases. So as if one change is positive, we have an increase in potential energy, for example, the other one must be negative, so we would be losing kinetic energy, and the other way around. Now, there's a different type of a unit that we'll be looking at in these examples called an electron volt. Now, when we look at things like subatomic particles that are really, really tiny, the joule is a huge, huge unit, and it's more often convenient to describe these type of energy changes using a tiniest unit called an electron volt. Now, 1 electron volt, or 1 little e with a capital V, is the work done when an electron moves through a potential difference of 1 volt. So 1 electron and 1 volt, or 1 electron volt is the energy gained or lost by an electron moving through that potential difference of 1 volt. So 1 electron, 1 volt gives us 1 electron volt. So if we have a look at the following, if an electron of negative charge, which is negatively charged, we denote it with a little negative sign and a little e, moves through a potential difference of 300 volts, then the change in potential energy is going to be 300 electron volts. So 1 electron and the number of volts, 300 electron volts. Is quite easy. If a proton of charge positive e, remember equal and opposite, protons and electrons, moves through a potential difference of 2500 volts, then the work done in this case is going to be 2500 electron volts. 1 positive electron or proton, 2500 volt difference, 2500 electron volts. Nice and easy. So, and the same if we've got an alpha particle, alright, an alpha particle has positive 2e and 400 volts, 800 electron volts. A nitrogen ion, if it has a charge of negative 3, 50 volts, 150 electron volts. Really simple. So just to keep in mind that the electron volt is a very small unit, and if we're ever converting energy from joules to electron volts or back the other way, then the number of electron volts needs to be much, much bigger than the number of joules. So to convert from electron volts to joules, we multiply by 1.6 times 10 to the negative 19, and to convert from joules to electron volts, we divide by that. So that's just the charge of an electron. Just quickly looking at a quick example, if we've got an X-ray tube and electrons are accelerated across a potential difference of 30,000 volts, what energy do they gain and what is their final kinetic energy? So in terms of the energy they gain, they're going to lose some potential energy or have a change in potential energy, which equals the work, which equals the charge times the potential difference. That's from our big formula. We've just chosen the parts we need. So we know that charge, 1.6 times 10 to the negative 19, our potential difference, 3 times 10 to the 4, or 30,000 volts, gives us this number here in joules, and we can convert that into electron volts by following the steps from before and dividing it by 1.6 times 10 to the negative 19. Conversely, once we know that it's 1 electron going through a potential difference, you don't have to go through these steps. You can just go 1 electron, 30,000 volts, 30,000 electron volts of energy has been gained. And again, if they've gained 30,000 electron volts of energy, we're saying that this potential energy has been converted to kinetic energy because they've now been moving. They're now moving across the potential difference, and so our kinetic energy is going to be whatever the gain was as well. So again, 30,000 electron volts. So we'll have a few more questions that we'll practice. Make sure you've written your notes, and I will see you in class. That's all for this one.